Robotics is the interdisciplinary study and practice of the design, construction, operation, and use of robots. Within mechanical engineering, robotics is the design and construction of the physical structures of robots, while in computer science, robotics focuses on robotic automation algorithms. Other disciplines contributing to robotics include electrical, control, software, information, electronic, telecommunication, computer, mechatronic, and materials engineering. Robotics usually combines three aspects of design work to create robot systems. First one is the mechanical construction, a frame, form, or shape designed to achieve a particular task. For example, a robot designed to travel across heavy dirt or mud might use caterpillar tracks. Origami-inspired robots can sense and analyze in extreme environments. The mechanical aspect of the robot is mostly the creator's solution to completing the assigned task and dealing with the physics of the environment around it. Form follows function. Second is electrical components that power and control the machinery. For example, the robot with caterpillar tracks would need some kind of power to move the tracker treads. That power comes in the form of electricity, which will have to travel through a wire and originate from a battery, a basic electrical circuit. Even petrol-powered machines that get their power mainly from petrol still require an electric current to start the combustion process, which is why most petrol-powered machines like cars have batteries. The electrical aspect of robots is used for movement through motors, sensing where electrical signals are used to measure things like heat, sound, position, and energy status. In operation, robots need some level of electrical energy supplied to their motors and sensors in order to activate and perform basic operations. And the software program how a robot decides when or how to do something. In the caterpillar track example, a robot that needs to move across a muddy road may have the correct mechanical construction and receive the correct amount of power from its battery, but would not be able to go anywhere without a program telling it to move. Programs are the core essence of a robot. It could have excellent mechanical and electrical construction, but if its program is poorly structured, its performance will be very poor or it may not perform at all. There are three different types of robotic programs: remote control, artificial intelligence, and hybrid. A robot with remote control programming has a pre-existing set of commands that it will only perform if and when it receives a signal from a control source, typically a human being with remote control. It is perhaps more appropriate to view devices controlled primarily by human commands as falling in the discipline of automation rather than robotics. Robots that use artificial intelligence interact with their environment on their own without a control source and can determine reactions to objects and problems they encounter using their pre-existing programming. A hybrid is a form of programming that incorporates both AI and RC functions in them. Applied robotics. As many robots are designed for specific tasks, this method of classification becomes more relevant. For example, many robots are designed for assembly work, which may not be readily adaptable for other applications. They are termed assembly robots. For seam welding, some suppliers provide complete welding systems with the robot, i.e. the welding equipment, along with other material handling facilities like turntables, etc. As an integrated unit, such an integrated robotic system is called a welding robot, even though its discrete manipulator unit could be adapted to a variety of tasks. Some robots are specifically designed for heavy load manipulation and are labeled as heavy-duty robots. Current and potential applications include manufacturing. Robots have been increasingly used in manufacturing since the 1960s. According to the Robotic Industries Association US data, In 2016, the automotive industry was the main customer of industrial robots with 50% of total sales. 5 In the auto industry, they can amount for more than half of the labor. There are even lights-off factories, such as an IBM keyboard manufacturing factory in Texas that was fully automated as early as 2003. Autonomous transport, including airplane, autopilot, and self-driving cars. Domestic robots, including robotic vacuum cleaners, robotic lawn mowers, dishwasher loading, and flatbread baking. Construction robots can be separated into 3 types: traditional robots, robotic arm, and robotic exoskeleton. Medical robots and robot-assisted surgery designed and used in clinics. Agricultural robots. The use of robots in agriculture is closely linked to the concept of AI-assisted precision agriculture and drone usage. Mechanical robotics areas. Power source. At present, mostly lead-acid batteries are used as a power source. Many different types of batteries can be used as a power source for robots. They range from lead-acid batteries, which are safe and have relatively long shelf lives but are rather heavy compared to silver-cadmium batteries, which are much smaller in volume and are currently much more expensive. Designing a battery-powered robot needs to take into account factors such as safety, cycle lifetime, and weight. Generators, often some type of internal combustion engine, can also be used. However, such designs are often mechanically complex and need fuel, require heat dissipation, and are relatively heavy. A tether connecting the robot to a power supply would remove the power supply from the robot entirely. This has the advantage of saving weight and space by moving all power generation and storage components elsewhere. However, this design does come with the drawback of constantly having a cable connected to the robot, which can be difficult to manage. 16 potential power sources could be: pneumatic, compressed gases; solar power, using the sun's energy and converting it into electrical power; hydraulics, liquids; flywheel, energy storage; organic garbage through anaerobic digestion; and nuclear. Actuation. Actuators are the muscles of a robot, the parts which convert stored energy into movement. By far the most popular actuators are electric motors that rotate a wheel or gear and linear actuators that control industrial robots in factories. There are some recent advances in alternative types of actuators, powered by electricity, chemicals, or compressed air. The vast majority of robots use electric motors, often brushed and brushless DC motors in portable robots or AC motors in industrial robots and CNC machines. These motors are often preferred in systems with lighter loads and where the predominant form of motion is rotational. Various types of linear actuators move in and out instead of by spinning, and often have quicker direction changes, particularly when very large forces are needed, such as with industrial robotics. They are typically powered by compressed and oxidized air. Pneumatic actuator or an all-hydraulic actuator. Linear actuators can also be powered by electricity, which usually consists of a motor and a lead screw. Another common type is a mechanical linear actuator, such as a rack and pinion on a car. Series elastic actuators. Series elastic actuation relies on the idea of introducing intentional elasticity between the motor actuator and the load for robust force control. Due to the resultant lower reflected inertia, series elastic actuation improves safety when a robot interacts with the environment, for example, humans or workpieces, or during collisions. Furthermore, it also provides energy efficiency and shock absorption mechanical filtering while reducing excessive wear on the transmission and other mechanical components. This approach has successfully been employed in various robots, particularly advanced manufacturing robots and walking humanoid robots. The controller design of a series elastic actuator is most often performed within the passivity framework as it ensures the safety of interaction with unstructured environments. Despite its remarkable stability and robustness, this framework suffers from the stringent limitations imposed on the controller, which may trade off performance. The reader is referred to the following survey, which summarizes the common controller architectures for C along with the corresponding sufficient passivity conditions. One recent study has derived the necessary and sufficient passivity conditions for one of the most common impedance control architectures, namely velocity-sourced C. This work is of particular importance as it drives the non-conservative passivity bounds in an C scheme for the first time, which allows a larger selection of control gains. Sensing. Sensors allow robots to receive information about a certain measurement of the environment or internal components. This is essential for robots to perform their tasks and act upon any changes in the environment to calculate the appropriate response. They're used for various forms of measurements to give the robots warnings about safety or malfunctions and to provide real-time information about the task it is performing. Touch. Tactile sensor. Current robotic and prosthetic hands receive far less tactile information than the human hand. Recent research has developed a tactile sensor array that mimics the mechanical properties and touch receptors of human fingertips. The sensor array is constructed as a rigid core surrounded by conductive fluid contained by an elastomeric skin. Electrodes are mounted on the surface of the rigid core and are connected to an impedance measuring device within the core. When the artificial skin touches an object, the fluid path around the electrodes is deformed, producing impedance changes that map the forces received from the object. The researchers expect that an important function of such artificial fingertips will be adjusting the robotic grip on held objects. Scientists from several European countries and Israel developed a prosthetic hand in 2009. Called Smarthant, which functions like a real one, allowing patients to write with it, type on a keyboard, play piano, and perform other fine movements. The prosthesis has sensors which enable the patient to sense real feelings in its fingertips. Thanks for watching.